Welcome to my classroom. In this video, I continue my discussion on mass point. I'm going to use mass point to prove two well-known theorems. They are Ceva Theorem and Menelaus Theorem. The two theorems give the equivalent conditions for concurrent lines and collinear points in a triangle. I first prove some interesting properties which will be used in the proofs of the two theorems. When the line segments inside a triangle intersect at the point, and the point divides the line segments in a ratio of the form of r/1, we have the following results. Here, G is the point of intersection of the line segments from the three vertices, and the ratios are denoted by r1 to 1 from A, r2 to 1 from B, and r3 to 1 from C. Then we have the ratio of the three sides which are given by these r plus 1, like AF to FB equals to r1 plus 1 to r2 plus 1. In part B, we have the product of the three r minus the sum of them is always equals to 2. You may pause the video and make use of mass point to prove the lemma on your own first. Regard the intersection point G as the center of mass of the triangle. To fit the ratio of lengths on AGD, assign a mass of 1 to A and a mass of R1 to D. Then the mass of G is R1 plus 1. Consider the ratio on the line segment BGE. The mass of B is the total mass times the corresponding ratio of the side. Therefore, we have AF to FB equals to R1 plus 1 to R2 plus 1. Similarly, the other two results can be obtained. That is, BD to DC equals to R2 plus 1 to R3 plus 1. And CE to EA equals R3 plus 1 to R1 plus 1. So part A is done. From part A, we have the mass of B equals to R1 plus 1 over R2 plus 1. Similarly, we have the mass of C equals R1 plus 1 over R3 plus 1. Consider the ratio on line segment AEC. The mass of E. Add up the masses as two ends. Consider the masses on the line segment BGE. We add up the masses as 2n for the total mass of the side. So we got this. Further simplify, we have an elegant result. The product of R1, R2, R3 minus the sum R1 plus R2 plus R3 is equals to 2. Ceva and Menelaus theorems can be deduced with this lemma. Here is the Ceva theorem. It gives a necessary and sufficient condition for three concurrent line segments drawn from the vertices of a triangle. In triangle ABC, AD, BE, and CF are concurrent if and only if AF over FB times BD over DC times CE over EA equals 1. Suppose AD, BE, and CF are concurrent. Let them intersect at G, and regard G as the center of mass of the triangle. Denote the ratio like the one in the lemma. By lemma A, we have AF to FB equals to R1 plus 1 to R2 plus 1. BD to DC equals to R2 plus 1 to R3 plus 1. And CE to EA equals R3 plus 1 to R1 plus 1. Substitute the result into the product. The product is 1. The first part is done. Now, consider the other side. Suppose the product is 1. To show three line segments are concurrent, we first consider two line segments. Let AD and BE intersect at G. Join CG and produce meet AB at F prime. So AD, BE, and CF prime are concurrent. Therefore, we have the product AF prime over F prime B times BD over DC times CE over EA equals 1. Combine the result, we have AF over FB equals to AF prime over F prime B, and thus AF over AB equals AF prime over AB. As both F and F prime are points on AB, we have F equal F prime. That is, CF passes through G. In other words, AD, BE, and CF are concurrent. The theorem is proved. Here is the Menelaus Theorem. It gives an equivalent condition for the transversal FD cutting the produce of AC at E. That is, in triangle ABC, DEF are collinear if and only if AF over FB times BD over DC times CE over EA equals 1. Note that in the third ratio, CE and EA are in opposite direction. So some version of Menelaus Theorem use -1 to stand for the product, indicating the opposite direction in the ratio. But we consider the lengths of the line segments only, so we take 1 here. Here is the proof of the first part. Suppose DEF are collinear. We try to draw lines to change the diagram similar to the one in the lemma. So we join BE and AD. Let AD produce meet BE at G. For triangle ABE, regard D as the center of mass of the triangle. Denote the ratios on triangle ABE same as the ones in the lemma. So we put down the ratios out 1 to 1, out 2 to 1, and out 3 to 1 as shown. Use these R's to represent the ratios in the statement. First, AF over FB. By lemma A, we have this ratio equals R1 plus 1 over R2 plus 1. Then BD over DC, which is easy, and it is what we denote by R2. Now, CE over EA, it is a bit complicated. First, by lemma A, we have EC over CA equals R3 plus 1 over R1 plus 1. Let us consider the ratio EA over EC first, and split it into 1 plus CA over EC. Substitute the result above and simplify it, and take the reciprocal. So we get CE over EA equals R3 plus 1 over R1 plus R3 plus 2. Combine the result. Use lemma B for simplification. After the simplification, then the result is 1. The first part is done. The second part. Suppose AF over FB times BD over DC times CE over EA equals 1. The argument is similar to the one of Ceva. That is, let F prime on the side of AB such that DEF prime are collinear. Because collinear, we have the previous result. That is, AF prime over F prime B times BD over DC times CE over EA equals 1. Combine the two results. We have AF over FB equals AF prime over F prime B. Therefore, we have AF over AB equals AF prime over AB, as Both f and f prime are points on AB, and therefore f equals to f prime. That is, D, E, F are collinear. The theorem is proved. The two theorems are proved by the use of mass points with ratios and calculation. In fact, the theorems can be proved by ratio of areas and similar triangles. You may prove the theorems again as an exercise. Also, you can use Ceva Theorem to prove the concurrency of medians, angle bisectors, and altitudes of a triangle, as suggested in my previous video. Try and enjoy.